Separation techniques. Separation techniques. Now, recall that mixtures contain two or more constituents, which of course we said can easily be separated by physical means. So it is this um, means of separating these mixtures that we are considering now as separation techniques. So the first separation techniques or technique we're going to consider is chromatography. Chromatography is the separation of the components of a mixture that is colored, by slowly passing the mixture over a material like paper, which absorbs the components of the mixture and separates them out individually as this mixture passes or moves over the paper, the medium. Okay, like I explained the other time, we carry a colored component like ink, and then we put on paper, and then let this paper, put one end of the paper in a solvent. Now as the solvent moves over the paper or the mixture also, the paper absorbs the components and separates these components out individually as they are moving over this medium. Now, the property that makes it possible, that enables the separation using paper chromatography, is the difference in the absorptive or retentive rates of the components. Because the different components of that colored mixture absorb, the paper absorbs it with different, its absorptive component is different, retentive component is different from the other components, or the other, yes, components of the mixtures. So because of that, they separate out. All right, so I'm saying the property used in chromatography is absorptive or retentive rate of the different components. The second separation technique we're going to consider is simple distillation. Of course, distillation is of two types. We have simple distillation, we have fractional distillation. We'll look at the simple distillation first. Now, distillation generally is used to separate mixtures that are composed of two or more pure liquids that has a wide range of boiling points. Now, what happens here is that the components of the mixture will be vaporized, then condensed and separated, isolated. Okay. Now, what I'm saying is, we have a mixture of, for instance, water and say kerosene. I mix water with kerosene. Remember that kerosene, the boiling point of kerosene is not the same as the boiling point of water. Am I using boiling point? Is when something boils that it starts evaporating. Okay. Remember I said vaporization. When it boils down, it starts changing to vapor. When it changes to vapor, then that vapor can be condensed and sent to one part. So when it's, if the boiling point of kerosene is lower than that of water, of course, then water will start evaporating first. When it evaporates, it is condensed. The gas that is coming out is condensed and then isolated. Then kerosene has been gotten out. And when it's 100 degrees Celsius, water will start boiling. You collect that one also, condense it, and then isolate it also. See, you've separated the water from the kerosene using simple distillation. The difference between simple distillation and fractional distillation is that simple distillation will only be able to separate out these different components if the two competing components, the two components that are to be separated, have a wide range of boiling points. What I mean is, the difference in boiling point between the kerosene, for example, and the water should not be very small. Let's say water is 100 and kerosene is 70, and that's 30. The difference is 30. Is wide enough, so simple distillation can distill it and separate them out. But what if the difference in boiling point, the boiling point of water is 100 and let's say kerosene was 95? Okay, simple distillation cannot see that difference as enough to separate them out differently. So kerosene may still come out with water, and water may still come out with kerosene. In that case, we need a fractional distillation. All right. So fractional distillation is used to separate miscible liquids which have close difference in boiling points of the components. But remember that for fractional distillation to be effective, the difference in boiling points between the two or the different fractions must be more than 10 degrees Celsius. So it cannot be like that 95 and 100. Even fractional distillation will not be able to separate them out. So it must be at least 90 and 100, 80 and 70. The difference should be 10 at least for fractional distillation to work. Then for simple distillation, it should be up to 20, 30, 40. Okay, but they are both distillation. What is used in crude oil in the refinery is fractional distillation to distill and separate out the different components that make up crude oil. So crude oil is put in the distillator or the chamber, and then when it's heated at different temperatures, the different fractions will start evaporating and is collected on different tanks. That's fractional distillation. All right. So generally, I'm saying that the physical property that makes it possible for simple distillation to take place is wide difference in boiling points of the components. Remember, these are miscible liquids that can mix up together like the coke and water. Or you can say that the property is difference in physical states. If you are having solid, liquid, right? And then that's the whole thing for distillation. All right, let's check the next one. Crystallization. Crystallization is used as a purification technique, for solids. Now we have crystalline solids, we don't have crystalline liquids. Crystallization is for solids. Now, an impure solid is dissolved in a solvent and then it is heated. You heat it until it boils. If the hot solution, remember solution is solvent plus solute, what you dissolved in the water is the solute. What dissolved the solute, as example the water, is the solvent. Solvent plus solute equals to solution. All right. So an impure solid, the solid is the solute, is dissolved in a solvent. The solvent can be water, and then this thing that the solid and the solvent is the solute and the solvent forms a solution. The solution is heated till it boils. If the hot solution is allowed to cool slowly, now you see the crystals of the solid will form back. All right. I'll give you an example. If you put salt in water and dissolve it, then you carry this solution of salt and water, salt solution, and then put in a kettle and start boiling. If you boil and boil and boil and boil until some water has left the kettle, then bring it down and allow it to cool. Open it. You will discover that some salt will start forming at the bottom of the kettle. The salt that had already dissolved has already started crystallizing back into the original form, the solid form, and start depositing at the bottom of the kettle, because the water that dissolved most of these salts has gone, so the salt has to come back to its other states. Remember, when evaporation takes place, only water, only the solvent is evaporated. Alright, so if you allow it to cool slowly, then crystals of the solid will form. Now the crystallized solid is higher in purity than the initial solid, which the impurities remain in the solvent. So the crystallized solid is then filtered away from the impurities. If the impure solid was obtained from crystallization process, then the second time of crystallizing is called recrystallization. That one that you allowed it to cool slowly and the crystals form back, that was called crystallization. If you are doing it for the second time to obtain the impure solid, then that is recrystallization. Now, in summary, I'm saying that crystallization involves heating to concentration for the solution, then you cool it, cooling, and then obtain the crystals. All right, so crystallization is driven by separation by solubility. So I'm saying the property that makes crystallization possible is separation by solubility. Solubility is the amount of solute that can be dissolved in a particular solvent. The amount of salt, like my example here, that can be dissolved in that water is solubility. So separation by solubility. Take note of it that cooling must take place before the crystals are formed. It's when you cool the solution that you boiled that the crystals will form. It won't form before you cool it. Alright, so the next separation technique is evaporation. Now, evaporation is used to recover a solid solute, like sugar, from a solution. That is, say you put sugar and dissolved it in water and it becomes a solution. You don't see the sugar again clearly. If you drink, you taste the sugar. So how can I get back the sugar from that solution? You use evaporation. So the solution must contain at least a solvent. Of course, solution contains one solvent. The process involves heating the mixture until no more liquid remains. You heat it. Let's say you boil the solution of salt and sugar in a kettle. Keep boiling. I told you that when you are boiling, when evaporation is taking place, when the thing is turning to vapor, it's not the sugar that changed. It's only the solvent, the water, that is changing to gas and goes to the atmosphere. So if that's possible, if that's true, then the water will leave slowly until there is no water again. Since salt or the sugar did not evaporate too, the sugar will remain back inside there and you get back your sugar. So you see how you used evaporation as a separation technique. Alright, so in summary, we say heat the solution, the solvent escapes into the air, and the required solute is left behind. Alright, now table salt is obtained from evaporation of seawater. Okay, if you have seen how the salt you use in your kitchen is processed, they fetch water from the sea, some very saline sea. They'll pack water from it and pour the water into a place and then allow sun to heat that water body and evaporate the water, and then as the water is drying slowly, and by the time it dries off, salts, crystalline salts, will be deposited on the ground on the base of that place where the water was kept, and then they pack the salt. That's how table salt is gotten from seawater. Okay, so the heat comes from the sun in that process. All right, now I've been saying solution, though we'll still discuss this in another topic, but I said solution contains a solute. That's what is going to be dissolved in the in what is going to be dissolved, and also contains a solvent, what is going to dissolve something. Now that solvent part can be water, of course, can be oil, can be anything, can be honey. Now when the solvent is water, we call that solution aqueous solution. Okay, so this one they say, so maybe it's for babies, they can dissolve small other drug in a syrup for a baby to take. That's a solution, but that's not aqueous solution, because the solvent is not water. So in any solution where the solvent is water, that solution is an aqueous, aqueous, aqueous solution. And the next separation technique is filtration. Filtration. It is used to separate insoluble solids, solids that will not dissolve in water, from liquids. Let's say you put groundnut into water and stir and stir and stir it. The groundnut will not dissolve in the water, because the groundnut is not a soluble solid. It's an insoluble solid. But since you mixed it with water, and now say, okay, since it's not dissolving, let me get back my groundnut and water differently. What do? Filtration. Now, when we're saying filtration, we deal with filter paper in chemistry. Filtration is not put it in a filter, and what you call filter as a local person would be sieve. That thing using sieving out rice or whatever. That's not filter. All right, in chemistry. When we're talking of filtration, we're talking about using filter paper. So you pour the mixture into a filter paper, and then the filter paper has a porous, is porous, is a porous material. The liquid will pass through those tiny pores, and the residue will remain on the filter paper. So you filtered and you have your residue difference, and the liquid goes through. All right, so the technique here is separation by particle size. The particle of the liquid is tiny and can pass through the pores of the filter paper, but the particles of the residue is bigger than the size of the pores, so it stays behind, it stays on the paper. Right, so the technique here and the property used here is separation by particle size. The next separation technique is centrifugation. Centrifugation. This one is used to separate a solid liquid mixture that is stubborn to settle. Yeah, you know that kind of thing. Forgive me for saying, let's say you put kata in water and then you try to make it mix. It doesn't mix, right? Or something like pap. It doesn't mix. You stir and stir and stir and stir. It won't mix. Please don't get irritated. Just trying to make sure I give you a very good example to imagine. You then see that the kata is stubborn, cannot mix up well. Now, centrifugation can help you to separate out and get back the kata, from the liquid. Now, how does that happen? All right. Now, the sample is placed in a centrifuge tube. Just imagine a centrifuge tube like a test tube. So you put the sample into a test tube and then connect it to the centrifuge. So the machine will spin the test tube, and it spins is like you are shaking it vigorously, and then not shaking it vigorously, actually spin it so that the heavier solids will go to the bottom and settle. If it's the kata that is heavier solid, it will go down to the bottom and settle. So with that, you can easily decant, you can easily slowly pour out the liquid portion, and then the stubborn solid that you don't want to mix together will remain in the test tube. All right, So I'm saying the sample is placed in a centrifuge tube and spun. The centrifugal force forces the solid to the bottom of the tube, while the clear liquid separates out to the upper layer of the tube and is easily decanted. Decantation. So since I've said decantation, now let me talk about decantation. So the next one is decantation. Decantation is used to separate mixtures of immiscible liquid or mixture of liquid and solid, such as a suspension. This mixture of liquid and solid is what I dealt with in centrifugation. But let me give you a perfect example of decantation. Have you sipped Gary before? Now, if you have sipped Gary before, then you discover that you put the Gary in a plate or whatever you put first, and you put water or whatever you put first. Let's just use that. Let's not put granite and sugar and all those yet. So you put the water or Gary and mix the water and Gary together. And then, of course, the water will be more than the Gary. You say water don't pass Gary. Then when you do this, let's say it's Gary that has chaff. So the chaff goes to the top layer of the water and stays there. Now there are three layers at that point. The layer of the chaff is on the topmost layer. The liquid is at the middle, and in the visible liquid, the clear liquid is at the middle, and the solid, the Gary, is down at the bottom. It's only two parts of those layers you need. You need the liquid and the down, that's the Gary. So you have to remove that chaff part, the upper layer of solid. Now, the upper one is still solid, the chaff is solid as long as it's not liquid, and you can see the sizes. Those are solids. How can I remove this solid, the chaff that is up, from my Gary? You discover that common sense just tells you to slowly tilt the plate, and the top layer pours out slowly, and then it goes out completely, and then you have your clear liquid on the two layers now, the layer of the liquid and the Gary down layer. What you just did by slowly pouring out the topmost layer is called decantation. Okay, that's decantation you just did. All right, so in this process you carefully pour the liquid into a separate container while the solid or the suspension remains. All right, example, say a mixture of sand and water. You can easily carefully turn out the water and the sand remains. Or let's say hydrated solution sulfates or sodium sulfate from an organic solution can easily decant, and that works. All right, so we get to the next one, sieving. Sieving, Sieving, and is used to separate solid particles of different sizes. Okay, this one you've also done it if you fried groundnuts before. Some people use sand in frying, some people use salt. I personally have used Gary before in frying groundnuts. Okay, whatever you use, whether it's sand or salt. So the salt is a solid. The sand is a solid. The groundnut also you are frying is a solid. So when you finish frying, you have a mixture of groundnut and the salt or sand. So you have two solids. You want to separate the two solids. You want the groundnut. You don't want to eat the salt. You want to separate them both. So that's where you use a sieve. Sieving is used to separate solid particles of different sizes. So if you carry a sieve and turn the whole mixture of the two solids of granite and salt or sand into the sieve and shake the sieve, the sand, which are smaller in size, will pass through the holes of the sieve and go out, while the granite, which are bigger sizes, will stay on the other side of the sieve. What you just did is called sieving. That's a separation technique. You just separated one solid from another solid. All right. So the mixture is placed on a sieve with a mesh of particular size. Um, the parts smaller than the mesh size of the sieve will pass through the sieve while the bigger particles remain on the sieve. Now, the last one we're going to consider to make it thin is sublimation. Sublimation is a process where a solid is immediately turned to gas. When that happens, we say it sublimes on heating. Alright, so the gas is then condensed and stored. That's what I'm saying. Let's say we have a solid that can sublime mixed with solids that cannot sublime, like iodine. Okay, you mix iodine solids, it's gray in color, with stones, other stones, and they have the same color, and you don't know how to separate them easily. And then you remember, oh, iodine can sublime. That means if I heat this whole solution, iodine will change to gas directly, but the stones will not change. So you heat the whole solution, the whole mixture of sand and iodine, which is a sublimable solid. And as you're heating this, the iodine will change directly into gas. You collect that gas, condense it, and store it. And then you see you've collected the iodine, separated them, it from the other solids that cannot sublime. So this method is used to separate a sublimable solid from a non-sublimable one. Example of sublimable solids are iodine, ammonium chloride, etc. Thank you.